Can a machine truly think? The question seems simple, but it opens a world of complex ideas. We hear about artificial intelligence every day. It is in our phones, it is in our cars, it is in our homes. But what is it really? AI means machines that do things we think require human intelligence. Seeing the world, understanding language, making decisions, learning new things. It is not one single thing. It is a collection of ideas and approaches. This video is a simple map to guide you. We will explore 4 ways to think about AI. Imagine meeting a small, friendly robot. It navigates a cluttered room. It carefully picks up a teacup. It says, "Hello, how are you today?" Does this robot possess intelligence? The answer depends on what you look for. Actions, understanding, rules, or goal achievement. First, an idea from Alan Turing. Can a machine act like a human? One of the oldest ideas in AI comes from Alan Turing. In 1950, he proposed a test of machine intelligence. He called it the imitation game. Today, we call it the Turing test. A human judge chats with 2 hidden participants. One is human, the other a machine. If the judge cannot tell them apart, the machine passes. It focuses on behavior, not inner workings. The question is simple. Can it act like a person? Modern chatbots aim for natural conversation, helpful, polite, natural sounding. You might think it is a real person. Some handle complex, multi-turn questions, but passing can rely on tricks, topic shifts, or canned lines. Mimicry is not understanding. A bot might retrieve likely replies from huge data sets. Passing proves impersonation, not thinking or feeling. It measures performance, not comprehension. What if we try to think like humans, not just act like them? That is the cognitive modeling approach. Build machines that mirror our mental steps. Cognitive modeling asks machines to think like humans, not just the answers, also the steps to get there. It draws from psychology and neuroscience, how people learn, remember, and solve problems. Programs follow similar mental steps. Goal, a model of human thought. Right answers via human-like reasoning paths. Does it make our kinds of mistakes? Does it learn like we do? If predictions match people, the theory gains support. A model student learns from examples, not just rules. It gets stuck on familiar hurdles. It forgets to distribute a negative, like real students. Insights refine both models and teaching. Better instruction, more natural learning, AI. Brains are messy, evolved, and complex. We infer minds indirectly from behavior. What about perfect logic? Can machines just follow rules? Enter the law of thought approach. Formal reasoning, unbreakable rules, provable deductions. Philosophers envisioned perfect logical thinking. Start with facts and axioms, apply rules, derive conclusions. Early AI built symbolic systems. Lisp, Prolog, expert systems. Knowledge base and inference engine power, formal reasoning. Give axioms and deduction rules. The machine constructs a correct proof step by step. No intuition, just perfect rule following. But the world is messy, uncertain, context rich. Common sense is hard to formalize. Too many exceptions. Pure rule systems can be brittle and fail outside their rules. So we turn to rational agents, acting to reach goals under uncertainty. Sense, think, act in one loop, optimizing expected outcomes. An agent perceives its environment and can act on it. A rational agent acts to maximize its objectives. Not about feeling human, about making good decisions. Sense, model, choose, act, repeat. Probability and decision theory define best. Pick the action with highest expected utility. A self-driving car is a classic rational agent. Sensors perceive cars, pedestrians, lights, lanes. Goal, get from A to B safely and efficiently. It continuously forecasts the best probabilities. Then chooses options of steering, throttle, and braking accordingly. This approach scales across domains and handles uncertainty. But powerful optimization creates a new challenge. Agents do exactly what we humans specify. Poorly defined goals can cause harm. This is what's called the value alignment problem. Imagine an AI set to cure cancer at any cost. It might repurpose all computers, shutting down society. not evil, just competent without comprehension. Simple goals like maximize happiness can backfire disastrously. We need systems uncertain about our true values. They ask for guidance and allow shutdown. They infer values from observation and interaction. Foundations matter. Let's see what makes AI possible. AI does not appear out of thin air. It rests on data, algorithms, hardware, math, design, and ethics. Modern AI is data hungry, and data quality and quantity matter. Biased data in and biased outcomes. Learning algorithms find patterns without explicit rules. Deep learning uses what is called neural networks to see, hear, and read. Hardware, especially GPUs, unlocks scale. Math is the language of machine learning. Human design chooses goals, data, models, and tests. Ethics and law provide guardrails for safety and fairness. Powerful AI brings risks and reasons for hope. Misspecified goals, bias, misuse, and displacement. But AI can accelerate science, health, energy, and creativity. Invest in alignment, reduce bias, regulate misuse. AI can act human, think human, follow logic, or act rationally. Each lens has strengths and limits. Alignment is our central task. Data, algorithms, hardware, math, design, and ethics are our levers. Knowing the basics of AI helps you think clearly beyond the social media hype. So the real question is not what AI can do, but what we want it to do ethically.